Yeah, it's a pleasure to introduce Lyal Harris from Institute National de Research Scientific. Lyal is originally from Australia, did undergraduate work at the University of Melbourne, and followed with his master degree and PhD in France in Montpellier, in Rennes and Montpellier University. And when he was on the faculty at the University of Western Australia for 15 years before taking some time working as a consultant. And after it, he joined Institute National de Research Scientific. And his, the tools he uses is geophysical work and structural geology. And with this, I pass word to Lyal.
Okay, no, thank you. And today, as Alex was saying, I'm building on from what Jean was saying last week and showing some geophysics and mainly on the Superior Province, but I'll also start off with an example, just like Jean did in the Pilbara, just to give a comparative idea. So, sorry, I realized that it had gone on to mute, so excuse me for that. I'll start again saying that I'm just moving on from Jean in talking about the geophysics of the Superior Province and also a little bit about the Pilbara. So most of you, if you're geologists, are probably used to seeing seismic data, and you'll be aware that with seismic data, you can see representations of the Earth in cross sections. But in the modern 3D data, we can also produce depth slices. And that is also the case from aeromagnetic and gravity data. But for a lot of geologists in North America, they don't realize that. And some of the view of geophysics that a lot of you may have is just a whole lot of equations, even with really good course notes such as these. For a geophysicist, you may have some problems in understanding the methods that are used. So I'm going to start off just with some very simple examples just to show the techniques that I'm using. And starting off, if we're looking at aeromagnetic data like I'll be showing later on, or gravity data, that what we're seeing if we look just at the original total field images such as this in the Western Superior, just like a cocktail, that we see the values that are being portrayed in these images that arise from a range of depths from the surface just down to the depth called the Curie depth when we lose the magnetic signal. So what we're really looking at as an analogy I'll use is just like a cocktail where you're just seeing the result of mixing a lot of the individual ingredients. So to give an idea about what this data can tell us, we convert that data into the frequency domain using a forward fast Fourier transform, and we can look at the energy of that data. And here, the top graph that is produced in the software that I'm using for processing geophysical data is showing on the vertical axis the log of the power of the signal against the wave number, if we like here, like the frequency of the data. And from the slope of that graph, we can get an estimate, as in this bottom figure, about the different source depths that are contained in that data. So again, just looking at the distribution of all the ingredients in our cocktail. So we can go a lot further using that these graphs, and so we can look at changes in the slope of this radial average power spectrum, where the steep slopes correspond to the deep or long wavelength sources going through intermediate source depths to shallow sources, and eventually where the curve flattens out, just noise. So if we enlarge this area in the bottom left, what we can see is that we can actually take out the long wavelength component here going down to the Curie depth of about 38 kilometers and separate these different components. And so what we're essentially doing with this power spectrum based filtering is extracting the different ingredients that make up that cocktail that the geophysical data is. If you want to see a little bit more about that, there's a great YouTube video without any mathematics. Just Google unbaking a cake and Fourier transforms and you'll get an explanation. So as Jean pointed out last week, if we look at the size of the Superior Province here, just shown in Canada, continues into the northern US as well, compared to the Pilbara here in the eastern Pilbara, it's the same scale. The Pilbara is just a lot smaller and a lot less complicated. And so what I'll start off is showing an example from the Pilbara in the eastern part to show the application of these techniques for separating the data before I then move on and show you two areas in the Superior Province. So again, all of you are probably aware of the classical geological maps of the Pilbara showing in pink these diapiric granite gneiss domes, and between them in the green colors, the greenstone sequences with a lot of basalts, which are more magnetic and denser, forming synformal keels. And so if we go and look at the geophysics for that area, at first glance, people might have been put off if they've ever just looked at the standard websites, such as here from the Geo Survey of Western Australia, where you think, well, you really can't get much information out of that data here, especially gravity, these fuzzy images that you can download off their website. And the magnetic data, again, if you look at the total field, it's just swamped by these highly magnetic areas, the volcanics, compared with the less magnetic areas around it. But what I'll show is if we start processing that data, just like I showed you, and separate these different components, we can see a lot more in the data, and even a lot better images can be produced than in the standard first vertical derivative, 1VD, that's often used in processing the data. And so what we can then see in the magnetics are these magnetic highs for the more magnetic volcanic units in the greenstone belts, these very large units through here. And these are wrapping around gneiss domes and granite gneiss domes in the Pilbara. So we can get a much better feeling of the geology and see that apart from the diapirs, we've also got refolded folds, as Richard Blewett pointed out a while ago, and especially in this area through here. From the gravity data, again, if we take out the components from closer to the surface, what we can see is in color, the changes in density of these different domes, the excuse me, less dense granites and the denser greenstones. And just superimposed on that is the gradient of the aeromagnetic image in gray, the tilt gradient, just to highlight the features. So we can get a lot of details that match the surface geology. And just if we look at this, these couple of cross sections from Collins et al. Through these domes, what we can see again are these different granitoid and gneissic units that make up our diapirs, these domes, and we can see these large high density anomalies with all the greenstones in these pinched synforms. But an important thing, and the reason I'm putting up this image of Bill Collins, is that in his image he's showing that the lower crust is actually preserved, and what we're seeing in the mid to upper crust matches in Bill's model, just like we see in this numerical simulation, where if we have these denser mafic units over granitoids, we can get this overturn of the forming our diapiric structures, leaving the more competent lower mafic crust intact. So any structures in that would be preserved. And so if we go back to the aeromagnetic data, that can be processed now to go and look at the features beneath these diapirs. And what we can see then as an image, we can just see a few ghostly outlines of where our diapirs occur. But this processing is highlighting different domains in the deep crust. And what we can see again is that apart from just the domains, we can see some regional scale faults that are occurring beneath these diapirs that we know so well from the maps. And again, if we like just comparing another two sets of images, that was the image I showed you before of the magnetics just for the upper crust. So we can drape that in gray over another image in the pale colors for the deep crust and see how the geology is completely different at the near surface compared with what is happening below, where we can see these regional scale faults. And with gravity data, we can even go deeper. And so in this data now, taking out a really long wavelength component of regional gravity, that the source depths are between about 40 and 120 kilometers. So whilst these calculations of depths are fairly imprecise, they're giving you a rough idea of the range of the signal is lying within the upper mantle. And so we can see these quite large regional domains on the left, draped over in grey just on the regional gravity, and just keeping that outlines of the regional geology, and keeping the outlines just of the geology map here in black, highlighting Mount Edgar and Corona Downs batholiths. We can see that these domain margins go completely oblique and to what we're seeing at the surface. But when we look at where this large dike, the Black Range Dolerite dike, that's a feeder to some of the Mount Rowe basalts in the Fortescue Basin, lies, we can see that that is occurring directly on the margin of this mantle domain. So there is a direct link between what we're seeing here in the upper mantle and features that we do see within the crust. So that's showing that how we can separate that information in different components in an area where it's much clearer, given that the nature of the diapirs. What I'm going to do now is show you two areas in the Superior Province. So I'll be starting off here in this first area, straddling the boundary between this older northern Superior Proto-Craton and the younger southern Superior, and then go and look in the western Superior. So if we look first of all at this northern Superior here in these more pale orange and fawn colors, what we can see two high-grade Mesoarchean terrains that contain in the Hudson Bay terrain here in the darker coloring rocks up to 3.8 GA. And these two different high-grade terrains are thought to have docked somewhere between about 2.76, 2.74 GA. And superimposed on these older terrains after they docked are a series of Neoarchean volcanic and sedimentary belts that are trending here in the northern Superior, more north-south. So this older northern Superior constitutes then what we call the northern Superior Proto-Craton. And just looking westwards through a 3D model where the colors are showing isosurfaces of seismic velocity difference with respect to a standard Earth model, it shows basically that in the northern Superior, this Proto-Craton is an entity that has a very deep lithospheric keel down to about 240 kilometers. And so the southern Superior is developed on the margin of this elliptical domain that's showing up in the seismic tomography. We see areas that still have some evidence of Mesoarchean rocks, but overall, looking at these different sub-provinces, we see more east-west trends of the sub-province boundaries, and the standard model is that these were east-west trending arcs and back arc basins that were successively accreted from north to south onto this older Proto-Craton margin. So in the northeastern Superior, what we can see here is that there, in the subduction model, we see 3 different subduction zones that have been proposed by Percival and Skolsky. But when we go and look at the long wavelength gravity, what we can see is that there's really no evidence for any subduction zones, or really that the upper mantle is agreeing with what we're seeing about the nature of subprovinces in the upper crust that are mapped. And so these colors here are showing domains in the upper mantle, the warmer colors here being more denser units. And what we can see is that sometimes, such as in the Ashwanapi, that these upper mantle domains match pretty well the contacts of the subprovince. But sometimes what we can see is this same domain continues beneath another subprovince, is only halfway across through the open arca. And we can get this other domain here, which is straddling part of the contacts here between the Nemesco, Opatica, and Abitibi. And so generally, when we look at this, what we can see is it appears that these domains in the upper mantle can be placed back together, that they've actually formed due to rifting of a more continuous domain. And so there's evidence here for 2 sets of rifts. In white, the arrows showing here those that were thought to be in the Archean, and then we've had younger rifting off the superior margin during the Paleoproterozoic in the Grenville province. And so what we can do then is, just like pieces in a jigsaw puzzle, go and put these back together. And so what we can see then is that we can fit all these pieces back in the mantle, showing that it's not accretion of different terrains in the Northern Superior, but in fact rifting. And that agrees with the geochemistry here of Anne-Aurélie Sapin, who's analysed the volcanic rocks in part of the Le Grand sub-province. And what she's interpreting is that there were 2 episodes of rifting that she's attributing to mantle plumes or some mantle upwelling for the Le Grand with these different ages. And she draws a cross-section here that the Le Grand sub-province is actually formed in a rift, which agrees with what we're seeing for the evidence of rifting in the upper mantle. Now, if we look at some these fantastic 3D, or essentially 4D, 3D with time numerical models from Maria Fischer that she did at ETH for her PhD thesis, what Maria is showing is an evolution from the early purely vertical or drip style tectonics through an intermediary stage into modern plate tectonics, where we have subduction zones where rigid oceanic lithospheric crust is subducted. But what we're looking at now in the upper mantle in the Northern Superior is just like what we see here in the red, this upper mantle domain in Ria's models. So if we look through one of her models that she's kindly sent me these slices of, but 2 depth slices through here, the red being the upper mantle domains, what we can again see is areas of that have been preserved throughout the evolution of her model. And in blue are areas that correspond to regions above where there's been dripping, either as sheet-like drips or cylindrical drips. And so if we compare these models of Ria's with what we're seeing in the Superior, what it looks like is that these domains might actually represent the same as the red domains in Ria's models. Now, this rifting in the Northeastern Superior continues after the Le Grand, and this is a cartoon from Nathan Cleaven and co-authors showing now for the Opunaka the continued rifting and uplift of the Le Grand and Minto sediment shedding into this rift basin in the Opunaka at a slightly younger stage. So we can explain the geometry here for the Northeast Superior in terms of continual rifting. If we look at the second area now in the Western Superior Province, we can again see evidence that goes against the standard models for plate tectonics. So this is again Percival's model for the Western Superior, again showing a whole series of subduction zones that John pointed out last week. Very difficult to explain that we've had so many different subduction zones at a scale that doesn't really fit with what we know. And anyhow, Jean went through this explanation again, showing that that requires multiple wide ocean basins, small continents, and that close in an exact north-south sequence at these very short time intervals. What we see in the geophysics is completely against this subduction zone model. Even if we look at the geology, and here just showing the geology of the Western Superior in Ontario, what we can see is that right across all of the Western Superior at about 2.73, 2.74 GA, there's evidence for rift-related lithologies. So we can see both in the north here that we're getting the intrusion of mafic-ultramafic rocks in what is referred to the Ring of Fire, or this McFarland Lake greenstone belt, showing here in green, going right down through into the Wawa Abitibi, and again 2.7 to 2.74 volcanics. And especially in the blue, we have the sedimentary sequences, just like we saw in the Opunaka in the Northeastern Superior, 2.738 GA volcanics and sediments. So coming back to this same aeromagnetic image that I showed you just in the introduction, if we look now at both Ontario and at Manitoba, we can see just in the initial total field magnetic image, the general trend shown by the more magnetic rocks with the warm colors and the less magnetic rocks through here in the blue colors. They're trending more east-west, especially in the south, to west-northwest, east-southeast. We can see some shear zones up here in the margin of the Hudson Bay terrain trending more northwest, southeast. But if we use the same processing technique that I showed you for the Superior, and we go now and look at longer wavelength components, this is a depth slice from about 10 to 50 kilometers. So we're going from 10 kilometers essentially to the Moho in this slice. What we can see now is a totally different picture where we can see, and I'm just showing here 4 of the major concentric features which are developed right on the southern margin of this northern superior Proto-Craton. Now, each of these concentric features is intersected by some linear features, shown here by the yellow arrows. I'll just point out a couple of these. We can even see that some of these faults that are interpreted that intersect the concentric features are even offset dextrally along some subprovince boundaries. And so what we're seeing is deformation that has taken place again across the entire Western Superior, associated with concentric features which haven't been recognized before in surface mapping or just in the standard enhancements of the geophysical data. And I won't show today due to time, but we can see these concentric features in other data sets, that we can see them in the gravity data as well as the magnetotelluric data. And the magnetotelluric data, even though it's very low resolution, also suggests that these concentric features can be seen in the upper mantle. And in fact, with some features rising up from the upper mantle beneath these concentric features. So if we look now at 2 areas, I'll first show a zoom in on this easternmost concentric feature in the Ring of Fire area. And then I'll show another enlargement here going from this concentric feature, cutting down across the Red Lake gold camp. So if we look at the geological map in the Ring of Fire, what we can see, the actual Ring of Fire that's known for those looking at mineral exploration, for its mineral potential. We can see here the ring of claims that have brought a lot of attention to this region, that this is just part of a much larger structure when we look at the age of these in the dark blue, purplish blue, mafic-ultramafic intrusions. All the intrusions the same age of the Ring of Fire occur within this outer ellipse of the structure interpreted from the long wavelength data. So there's a direct link between what we're seeing at the surface from the intrusions and these features in the deep crust. But when we look at the aeromagnetic data enhanced to be looking close to the surface, the actual Ring of Fire, again, just to orient you, is through in this position. What we can see are just the regional trends right across the Western Superior, from east-west through to these northwest, southeast trending ductile shear zones, that we don't see any surface evidence for the concentric structures. So they would lie here in black. So what it's showing, there must be some decoupling between what we're seeing at deeper crustal depths from the long wavelength component and what we're seeing here in the upper crust. Now, trying to explain this, I'm going to show some images of Venus. And as Jean pointed out last week, Venus is often used as an analog for the Archean Earth without plate tectonics. And so what we can see here, we've got some excellent radar imagery and altitude data here combined in this image of Venus. And I'll come back to this area just in a little moment. But if we look now at comparisons between Earth in the present day and Venus, On Earth, of course, as we all know, that we have plate tectonics, and one of the key elements, in fact, the defining element for plate tectonics is the presence of subduction zones. So we have this subduction zone in this cartoon with oceanic lithosphere, and subduction is creating these volcanic arcs. And looking just at this map now of the Pacific, a different ring of fire, what we can see is the arcuate form that's given here if we're looking at the depths of earthquakes, epicenters of earthquakes going from shallow in the orange through to much deeper earthquakes in the pink through to the reds. And so if we look at the results of subduction on Earth, we see these arcuate belts of volcanism, and we also get more linear belts where subduction has occurred at Andean type margins. But if we look at Venus, what we're seeing is a random distribution of volcanoes and also random distribution of coronae. These coronae structures, which I'll show an example of next slides, which are formed above mantle upwellings. And this map by Anna Golcher, also from ETH group, she's showing that some of these coronae are probably still active and others she's identifying as inactive. But like I said, completely different situation on Venus for the distribution of volcanoes and coronae, and there's no evidence anywhere on Venus for subduction zones. So if we look at what these coronae look like, this is a map now of Aaron Bethel from Carleton University, and this is one such corona through here, Fatua corona. And what we can see is something very similar, in fact, really identical, both in the geometry and scale of what I was showing in the Western Superior, where we get concentric faults and fractures here in the blue, intersected by regional faults shown here in red. And this geometry is interpreted that we're having mantle upwelling beneath Fatua corona during regional shortening. So hence we get one set of these structures instead of a whole set of radial structures being developed. And so Aaron has drawn this figure, which I've just showing you here, where a typical form of a corona with these concentric structures being developed above a mantle plume or any mantle upwelling. And if there's a regional shortening, these regional faults that intersect in that upwelling. And Taras Gary has produced these concentric structures in numerical models. And so these top figures from Taras's paper, and putting the example from the ring of fire that I showed you in the Western Superior beneath it, we see that these concentric structures in the Superior are the same scale and form as both on Venus and in the numerical models of Taras for developed above an upwelling mantle plume. And it's interesting to note that in Taras's models, he is also showing in the dark green where he would expect there to be crystallized mafic magma. That's exactly what I showed you for the geology map of the ring of fire, with the mafic-ultramafic intrusions occurring within the outer periphery of one of these concentric structures. Looking at the second example, and now this is in the western part of Ontario, straddling the border with Manitoba. And in this image, what I'm showing you is a comparison between, in red, the structures that I've interpreted from the long wavelength aeromagnetic image that are seen in the deep crust, comparing that to, in black, the faults that are mapped at the surface by the Ontario and Manitoba geological surveys. So what we can see is a completely different pattern of the structures that are developed at depth compared with what are at the surface. There are a few little hints occasionally of some features, such as a few curved faults through here that are matching a concentric feature around Lingham Lake. But overall, a large difference. We're not seeing these regional through-going faults. So if we look, where does this concentric feature lie? Well, in the map, what I'm showing you are two different levels through the Northern Superior Proto-Craton imaged here in 3D. So this is a 3D isosurface that corresponds to the margin of the Northern Superior Proto-Craton. The 1 and 2 here on the map are referring to, in number 1, where we have the surface projection of the southernmost extent of that Proto-Craton, and here 2, just where the margin of that Proto-Craton would occur closest to the surface. So what we see is this concentric feature is developed exactly on the margin of the southernmost extent. And so comparing with the coronae, where we have a mantle upwelling, the position of these mantle upwellings is controlled by the geometry of this more rigid and buoyant Proto-Craton. And so the concentric features are being developed along its margin. So just showing in a schematic view through here, what we can see is decoupling between the structures that we can see at the surface and interpret from the upper crustal components of any geophysical data. So in red, we have the main structures that we're seeing, a series of dextral transpressional shear zones, just being shown here schematically. In some areas, there's also been some normal faults, down-throwing blocks in preserving sequences such as interpreted from lithoprobe seismic in the Uchi belt. But as we can see, the pattern of structures here is completely different from this pattern, again, just shown schematically. If we just tear away the upper crust and look now in these deeper features where we see concentric structures which are interpreted to occur, as I said, on the margin of the Northern Superior Proto-Craton, intersected by these faults. And there is evidence for some of these structures to have been reactivated during the same event that created the features that we're seeing in the upper crust. And occasionally, such as number 4, we actually get faults that do occur above these basement structures, but not of a regional extent. And mineralization, most of the main gold deposits, I won't be going into in this talk, but they are occurring above these more north-south transverse faults and the intersection with these regional structures. So if we're looking at this model, we're seeing a completely different type of model compared with the standard creme brulee or jelly sandwich analogues that have been applied to explain strength profiles. Instead, what we have here is what in Quebec or in France called a millefeuille. In English, I think they're called Napoleon pastries, where we can get an upper rigid layer here of pastry, and then the second middle layer of pastry and a lower layer that correspond to the upper mid crust and upper mantle, and more ductile layers between. Why do we get this in the Archean? Well, it goes against what a lot of people think just when we consider the suggested higher heat flow in the Archean. And that is that with the higher heat flow, we've lost all the water from the deep crust, and we've extracted so much of the material. So we have intrusion of TTGs and pegmatites up into the overlying sequence. So we're left with an anhydrous deep crust. We can see, however, because of the difference in geology and the geometry of structures in the deepermost crust compared to the upper mantle, we must have also had, however, a ductile decollement, decoupling the deformation we're seeing in the long wavelength aeromagnetics from the sort of domains that we're preserving in the long wavelength gravity. So in other words, we're needing these two different decoupling horizons corresponding to the yellow, the crème pâtissière in the millefeuille example. So looking again at the how to explain this in the regional tectonic models, well, the numerical model of Koptev is suggesting that here, if we have a mantle plume beneath craton. In this case, I'm just labeling this the Northern Superior Proto-Craton. What we get is this plume is being deflected by that Proto-Craton, and we're getting rifting on the craton margin. And so that is the equivalent to what we're seeing in the Oxford-style domain on the southern margin of the Northern Superior Craton at about 2.73 GA, and also the timing for the mafic-ultramafic intrusions is again agreeing with this timing for rifting. So what I've done is applied that model now just in a 3D sketch to explain what we're seeing, with just showing 3 of these concentric features intersected by these transverse faults in the southern margin to the Northern Superior Proto-Craton. So what I'm interpreting is that we have a very large mantle upwelling, and of course the scale of these upwellings is such that it could be underneath the whole of the Northern Superior Proto-Craton, and if that upwelling is to the north of the keel to the subcontinental lithospheric mantle, that can induce the regional shortening that is required to produce just this one dominant set of structures that are intersecting concentric features developed over secondary upwellings associated with this much larger, more distant regional upwelling. So a quite complex geometry, but easily explainable if this upwelling through here is split up into a series of secondary structures on its keel. And so the model that we're proposing now is just like what Jean proposed in 2014 in the geology paper, that we're looking at plume-related rifting and fragmentation of this older Hudson Bay terrain, just preserving now here in the north, the Northern Superior Proto-Craton, and developing in these rifts the series of greenstone sequences. So to try and explain after that, how do we get the regional shortening? So it's one thing to show that we might be developing our greenstones and producing some of these structures in the deepest crust due to mantle upwellings. But if we look at any geological map, we see that there are regional folding and regional shearing across the Western Superior. So again, come back to looking at Venus because it's such a good example of deformation without plate tectonics. And so in that same image I showed you before, in Ishtar Terra, in the northern hemisphere of Venus, the northern polar view presented here, what we can see in an oblique view just based on elevation is that we get a high plateau, Lakshmi Planum, and to the northern margin of Lakshmi Planum, we get a series of mountain belts and a high plateau being produced. And Jean showed some examples of how that I've been able to map some of the shear zones around Lakshmi Planum in the last talk, so I won't go into any details. If anyone's interested, they can look at more at the recording of John's talk or at our paper on this. But if we look in map view to this fold belt that is developed to the north of Lakshmi Planum, what we can see are a series of structures where I'm highlighting interpreted reverse faults and thrusts. In the black color, a series of sinstral shear zones in red and dextral shear zones in green. And what we can see is that there's a change in the sense of displacement with sinstral motion on the western margin of Lakshmi Planum and dextral on the opposite margin. And we see a complex network of shear zones developing ahead. The geometry of structures that we can see through here is exactly the geometry that we get associated with the indentation of India into Eurasia and the lateral expulsion of Indochina. And we can again see the change in the centers of movement on these shear zones, indicating the lateral escape of this block to the east of Lakshmi Planum. And it's the same geometry that Gilles Peltzer and Paul Taponnier produced in these analog models of indentation of a metal ram into layered modeling clay. What Jean didn't show last week was that we can also see evidence for this indentation and a lot more if we look at the Bouguer gravity over this part of Ishtar-Terra. What we can see in the Bouguer gravity is, first of all, the blue areas here are low density regions, and the Bouguer anomaly here is calculated for the density of basalt. So to explain these, we must have some less dense material, and we're interpreting that as being very similar to continents on Earth, that there must be lower density felsic crust, whether that's going from northerzites through to granites. Until we get more information of the surface geology, we don't know. And immediately to the south of Lakshmi Planum, what we can see in red are these zones which are even higher density to basalt. So I'm interpreting that as that we've had upwelling of upper mantle, higher density, the basalt flows on the surface to produce these linear anomalies associated with rifting. And the stars in the center of some intermediate to low anomalies through here are where Richard Erst has interpreted mantle plumes. So if we put all this together, what we can see is just like in the Western Superior, we have a craton-like body through here, Lakshmi Planum, a rift on this margin, and the black lines are showing the edges in the horizontal gradient of the gravity data. These gradient edges refer to simply as worms, gravity worms, and their offset agrees also with this indentation model. So if we look in 3D and in 2D of crustal thicknesses, this again better shows how we've got this rift. So crustal thicknesses in blue, just like oceanic crust on Earth, and we have beneath these mountain belts here, thicknesses up to 50 to even 60 kilometers in Maxwell Monts that equate to chains like in the Himalaya, where we've got thickening of the crust. But in the gravity data, now I've just superimposed the main faults on this, and we can again see a consistent pattern. But especially if we look here in 3D, there's not just one sequences of rifts and displacements, but two. And we in fact see that the east-west rift south of Lakshmi Planum is cut by a whole lot of more north-south structures, smaller wavelength. So we're actually getting an orthogonal change. So Venus is not just some static body with occasional movements. We can see regional scale, uniform changes in horizontal stress, and the rifting in these regions is compensated for by thickening. So after our first indentation of Lakshmi Planum, Maxwell Monts is formed during east-west shortening, and this is compensating for extension in these more north-south rifts. So for the Archean Earth, Jean proposed this model of crotonic mobilism, where regional mantle flow, sometimes called the mantle wind, acting against these deep, rigid keels to Archean cratons, is responsible for the displacement of these cratons, causing deformation of greenstone belts and sedimentary basins on their margins. And if we look at what is happening in Venus, and also now in this model for the Western Superior, we can see that we can add an extra force to that model of just the regional mantle flow. Even if we look on Earth at the present time, and this is a 3D model now under the Afars, and looking here at the Red Sea Rift, that we get the Afar plume rising up and being deflected by the mantle wind. And so we get, again, increased horizontal displacement of this plume head. And that's partly responsible for the shortening that we're seeing in the Zagros. So we can add to this cartoon of Jean also the effect now for the Western Superior of having an additional force just of the mantle upwellings driving against this craton, causing the regional shortening. So what we're seeing here in all of this geophysical data is goes against completely the models for subduction and accretion. It's just impossible to explain the structures, I think, that I've been showing in terms of the conventional models. due to the homogeneity of a lot of these events and domains across the both the northeastern and western Superior, and there really isn't the position to put when we look at the upper mantle features any of the subduction zones that have been interpreted. And so what we're seeing instead is evidence for linked mantle upwellings associated with deep transverse faults and rifts, followed by and even during regional deformation. So in the Superior, we're seeing the same sort of deformation as on Earth. And so we're not seeing evidence for multiple subduction and accretion events. So basically in the previous studies, we haven't been looking at the right level, right depth in the crust, and we also haven't been looking at the right direction, and that a lot of the surveys are actually done parallel to the structures that we're seeing to be the most important. And so this research is showing that it's important to be looking not only here, but in other areas for more evidence of these concentric features that could be giving us evidence for mantle upwellings that haven't been seen until now. And I'll just finish off in putting in a plug that for those that are more interested in the economic implications of this research, that both Jean and I will be giving 2 talks coming up, mine on Thursday, well, so tomorrow evening in Quebec time. If you're wanting to see information and links for this, just Google GeoHub. It's in a series of talks in Australia. So I haven't looked at the economic implications here, but of course these new tectonic models have major implications also for mineral exploration in not only the Superior, but in other Archean terrains. Okay, so I'll leave it there. Thank you.
Great. Thank you so much, Lyal. We've got some questions for you in the chat. Much earlier on, Paul typed a question asking, a defining characteristic of plate tectonics is the presence of torsionally rigid plates. A surface manifestation of rigid plates is large-scale strike-slip faults. Such faults are absent ? On Venus, but Lyal showed them to exist in the Superior Craton. Should we take such faults as evidence for plate tectonics as suggested long ago by geophysicist Norm Sleep?
I would say definitely not, because what we can see on Venus is that in fact there have been very large lateral displacements along strike slip faults. And again, these faults, what I always like to see is that we just don't see them in one data set. We see them both in the radar data and in the gravity data. And so we're looking at really significant structures because of the low resolution of gravity, that if we can see these structures, they're affecting essentially the whole crust. So no, that what we're seeing is that these strike slip faults, certainly whilst they can occur, of course, as we know during plate tectonics, that plate tectonics is not essential, that it's all coming down to terminology. And of course, there's been this debate after Jean's talk as well. But what we're saying is a big difference from where we have the presence of modern style plate tectonics with the presence and the link, and in fact some of the major controls, as Jean has pointed out, of subduction zones on these displacements, and to separate that from this older form of crotonic mobilism where we still have displacement of these rigid cratons, but we don't see any evidence for subduction zones. So any material, as shown in that model by Ria, is returning to the lower mantle through the form of these mantle drips and not by rigid subduction zones. And so that's where, again, it's a distinction, but I think Ria's models show very well how we get a transition from just the purely vertical tectonics and dripping through to the modern stage plate tectonics. And of course, there's going to be a transition, but we just don't see any evidence for these arcs or back arc basins and this progressive accretion at all in the geophysical data as well as what Jean showed last week from the geochemical and petrological data in the Superior. So that's why, you know, we're proposing there's a completely different model both for Venus and for the for the whole of the Superior. So of course we can have some good discussions later on, Paul, at some stage, and with others, that we're saying that we really do need to have a talk about definitions and how to define what we're talking about. And so that we already had a large discussion at a meeting in northern Italy a few years ago that several people that have been in this group with Taras and others organized through there. And again, that's the main thing that was pointed out was this necessity to have develop a terminology that really defines what we're meaning by these different events. Different processes.
Popper said to scientists, do not get involved in arguments over definition.
Yeah. So that's where I'd just like to point out there are differences through here, and that it's just for me very hard to explain, and especially when we're looking at these upper mantle features, that the fact that we can just shove these back together perfectly in the northeastern Superior, they're not as easily moved back into place, if we like, in the Western Superior, but then in the Western Superior we're seeing a lot more of this evidence for the secondary mantle upwellings that have really disturbed that, and so probably a lot more dripping occurring to compensate for those upwellings. But no, I'm certainly open for other interpretations. It's just that geophysical data is just telling a different story. That's what I'm seeing that needs to be explained.
I guess it depends on the geophysicist.
Well, it's again, I'm using techniques that these are nothing new. It's just that they, for some reason, the techniques that I'm using that I first learned in the late 1980s in Australia just haven't taken on in North America. So the separation and this depth slicing that I'm using is a standard technique and is used by most mineral exploration companies. It's just in the academic world, it doesn't seem to...
it certainly is by every geophysicist I knew at the Geological Survey 40 years ago.
Yeah, so there's been more in the past and everything there, but it's just now that you talk about depth slicing and show this. And so now but it's also now we've got such fantastic new data and different data sets that we can, you know, really get a lot more out of that data. And for the Geo survey mapping, of course, everyone has been more focused, and rightly so, on looking at what can be related directly to the maps that they're preparing of the upper crust, the surface.
All right, we've got another question from Catherine Bethune. In a classic accretionary origin, for example, Canada Cordillera, as imaged by lithoprobe transect, isn't the crust decoupled from the upper mantle? Terrains are essentially flake-like entities that have been accreted and translated horizontally. Have you applied these techniques to modern orogenic belts in order to make comparisons?
Well, the example that Catherine was talking about there, that's actually a project of the GSC at the moment. That the group in Vancouver is to be looking at that, and it's Nathan Cleven. I showed an example there in the Northeast Superior. He's been working on these ideas for the Superior, and he's making that exact comparison. I personally haven't looked at the Canadian Cordillera. I have looked at some other origins, and such as in Australia, just very briefly, but we don't see the same sort of features exactly, you know, that we are seeing in the Archean. But no, that's a good point, though, that certainly a lot more needs to be done, and so really hope that this GSC project will come up with some information that will give us a much better feeling what the differences are between the Cordillera and what we're seeing.
Yeah, sorry, I'll just interject. I think it's important to apply your deep sort of depth profiling to a modern belt, because if you're uniquely applying it to the Archean, then yeah, I just don't see how some of the arguments can fly, because I mean, one would expect that the upper crust would be decoupled from the mantle and so you could argue, you know, the counter argument would be that this, you know, the superior upper crust is decoupled from the mantle.
Well, that's exactly what I'm saying, and but the difference is the scale too that I'm looking at, because if we look at this geophysical data right across the superior, we're seeing all these mantle domains that are at a high angle to what we're seeing at the sub-province boundaries. And so the main thing is not only that they are at a high angle, but they continue beneath what are interpreted as sutures, especially say in the Western Superior, in the Percival's models. And it just cannot be explained in that with the, say in the Western Superior, these linear sort of subduction systems that Percival has described, where in the mantle what we're seeing are features at a higher angle. Now, I mean, I haven't shown the mantle maps for the Western Superior yet. That data is not public because of some mineral exploration implications, but it's the same as we're seeing in the Northeastern Superior, that sometimes, as I said, that the margins to these domains fit, such as in the Ashwanapi with the sub-province boundaries, but we can't really explain the classical model of subduction and accretion of disparate terrains, where these mantle blocks continue right beneath what are interpreted as subduction zones in previous studies, such as showed that going from the Abitibi right up to the Nemesco, we just see these features that same features continue, and they only underlie part of each of these sub-provinces. And so it's not giving this simple idea of a whole series of discrete blocks that have been accreted there. It's a lot more complex, but it does match completely this intermediate stage between the modern day subduction and drip tectonics in Ria's models. So if you haven't seen any of Ria's models on her website, she's got videos of these models, and it's really informative to have a look at this transition in her models.
All right, I've got another from earlier from Bob Stern. What is the characteristic scale of drips and plumes of corona for Pilbara and for 2.7 billion-year-old Canadian shield?
Oh, look, I haven't looked, you know, at the Pilbara, I haven't done any detailed study. I've just quickly, well, basically following, you know, in Catherine's reasoning, I just wanted to look at whether what I was seeing was unique to the Archean and even unique to the Superior, but I haven't seen any evidence in the Pilbara for these concentric structures that I can link to mantle upwellings, the same as I've showed in the Western Superior. And it's early days, but I am starting to see some of these possible concentric structures in the Northeastern Superior, but I need to do more processing. I have looked at the slave craton and I haven't seen any there. So I can't really give any idea for the Pilbara, but what we're seeing across these upwellings in the Western Superior and on Venus, I don't think these are the main mantle plume, or if using Jean's terminology, instead of a plume that we're dealing with mantle overturn upwelling zone or ouzo, they would be at a much larger scale. But these secondary upwellings, we're looking at from 130 to say 200 kilometers, that sort of range across. And we're seeing that same sort of range in Venus coronae. And so that's also, you know, made me wonder where instead of getting a whole series of mantle plumes that are shown in Venus, whether a lot of these coronae on Venus could similarly be explained as secondary structures associated with a much larger upwelling. So it's an area that there needs to be a lot of work both by modelers and trying to get a lot more information, of course, in future missions to Venus. Now, I would point out that the terraces model also showed, as I said, the same sort of structure though for the mantle upwellings, but in some of Terrace's models also we're seeing that same geometry can be produced at even scales that are more compatible with some features such as Artemis, a much larger feature possibly associated with mantle upwelling. So even some of the numerical modelers would be much better to me to show what are the actual controls on the scales.
All right, Kent.
Oh, yeah, okay.
Put his hand up.
Yeah.
Yeah, so go ahead, Kent, if you'd like to ask your question, you can unmute.
Yeah, Lyle, we've had a lot of discussion about whether the Mesoproterozoic may have been different. And it seems to me, following up a little bit on Catherine's questions, that it's critical to really say something about what's going on in Mesozoic, Mesoproterozoic and Paleoproterozoic origins and compare these to what you're seeing in the Archean. And I was wondering, have you done any of that, and do you have plans to do that?
I have done that in several areas. We're in fact writing up one interpretation on the Southeast Churchill. Well, it's a paper by a former student, a master's student that I co-supervised. So we're waiting for him to get that out. But looking at the Southeast Churchill, I can't see any evidence for the interpretations that have been presented previously here in these talks. The Grenville province on
by the Southeast Churchill, do you mean the trans-Hudson origin, or?
Yes, yes. That when the Southeast Churchill is normally what we refer to in the past it used to be called the Ray, but it's on the eastern margin of the Superior Province in Québec. That is now generally referred to as the Southeast Churchill. But so I mean that is the one belt that I've looked at in detail, and in the process of writing up a lot of the geophysics on that. I'm also just finishing an analysis of the Grenville province as well, and using all the same data sets, looking from the mantle up. And so, yeah, I can't really comment on that just at the moment, but I've certainly was looking at these terrains because we need to obviously see what's happening there. And I have looked at one other younger belt again, just briefly, and that's Japan, just to see what do we see in a modern sort of subduction system. And there are similarities, but major differences as well, that everything is a lot more organized as one would expect to in the mantle in Japan. The only proviso there is that there may be fragments of the North China Craton that are rifted off that we're seeing in the mantle as well. But there are certainly major differences. I don't see the same sort of features that I've just showing there in any other younger belts that I've just given a cursory look at. But now it's early days, and there's been enough just to try and look at all this data in the Superior, the Southeast Churchill, and the Grenville. So we're in the process of writing that up. So I'll let you know when, and others know in this group, when that information is out, or at least becomes public. The Grenville data is not public just at the moment.
You said you looked at the Slave province. What did you find there?
Well, I couldn't see anything about what I've just been describing there. And I can't, basically I couldn't see any evidence for the major, for the lithospheric keel. And looking at, again, just looking very quickly at the literature, there have been other papers saying that the slave may have lost its lithospheric keel, and there's probably been a lot of younger modifications of the slave as well. But I mean, Catherine would be a much better person to answer anything about the slave. I know very little about it, but it was just in the same vein as people are saying. I just had some quick looks at first pass glances, and I couldn't see much of interest to me in the slave, but that lack of interest for me probably means that we've got something that's very important, and why is that different? And so, yeah, if anyone wants to follow up and using some of this data in the slave, I'd certainly be welcome to share that data.
Yeah. I think, Lyal, this is critical too, to look at some other Archean Cratons, like the Baltic Shield, for instance.
Yeah.
If you're going to generalize on this sort of model for the Archean,
yeah,
you've got to have more than one Craton, the Superior Craton, to generalize, I think.
Yeah, well, that's also why I wanted to show at the start, just briefly, something of the Pilbara, although it's older there, just that we can see these domains. But there's a big difference in looking at the Pilbara compared with what we're seeing in the Superior. In the Pilbara, there are just these blobs in these domains in the upper mantle that one can't see any link in, like sliding them back like I did for the Superior. So it's, again, would be really interesting to see how these features in the upper mantle from the long wavelength gravity change with age in the Archean. And that's where, you know, we've only just looked at two examples there, but unfortunately, of course, I can't look at much of the Baltic areas. Some of the data isn't available. Some of the long wavelength data isn't available over those areas. I could try with the existing data, but I haven't tried that.
Yes, thank you.
There was, yeah. No, I definitely completely agree with you, but I mean, this hasn't been published yet. I mean, these are most of this story related to the superiors coming out in a paper, just basically a report for the Geological Survey of Canada that funded this research. So no, we've definitely got to write this up, but also try to expand that to other areas as well. I totally agree.
Jean offered a relevant comment here. He said, to answer Kent, the Superior is perhaps the only craton large enough to reveal these big lower crustal blocks.
The other thing, there's Richard Ernst had his hand up before, following on from the Venus. So
yeah, he did. I think was relevant to the question from before, Kent's, right? Okay. Yeah. So Richard, if you want to go ahead.
No, thanks, Lyal. I caught only the last half of your talk, unfortunately, but it is exciting to see inclusion of corona into the story on the edge of the northern superterrane. And so just myself and our Venus research group, we've been doing a lot of thinking and work on corona, as you know. And so the range and size of corona can be from hundreds of kilometers, but actually, as you mentioned, all the way up to Artemis, but there's some that are, which is 2,500 kilometers across, but there's some that are, you know, a number that are in the 500 to 1,000 kilometers. So whether they're all the same kind of feature or not is obviously something to be thought about from definitions, but also modeling. One of the things I wanted to mention, though, is that Ken Buchan and I have been doing a lot of thinking about the nature of not only the radiating dike swarms, but also the circumferential extensional fractures, which we think are equivalent of circumferential dike swarms. So, and in terms of numbers, the number of corona on Venus is somewhere approaching 500. So an incredible number. Ken Buchan and I found so far only about 20 on Earth. But of course, this kind of geophysics is potentially revealing a lot more. So it's exciting kind of to bring it, the analogies of what we're learning from Venus to Earth, because Venus, you know, has the glory of no plate tectonics. So we get to see all kind of plume related, diaper related sort of structures. And just one final thing, you mentioned the work of Aaron Bethel, who's our PhD student. And so that kind of thinking with respect to Fatua corona, with the circumferential pattern, which was actually somewhat elongated in one direction, consistent with the radial stress pattern. And just want to mention that in her work, she's also been looking at the definition of corona, that they have this topographic, often a topographic rim and an outer annulus around that. But in many ways, the proper kind of definition, maybe the one that might be particularly relevant to Earth, is the full extent of the circumferential fractures, which can go way further out. So, but in the geophysics, you may be seeing structures that are potentially related to the sort of differences in topographic thickness. So maybe you're seeing some of the what would be analogous to the topographic structures on Venus, where you have thicker portions and maybe the gravity and the aeromag are slightly different because of thicker units of particular types, whereas some of the structures may go considerably further out. Anyway, that was just a little additional background, but certainly exciting to see these important features on Venus, this class of features on Venus being applied increasingly to Earth.
Yeah, that's one thing that it seems a little bit strange, but in Venus, you've got so much higher resolution radar data to be mapping these structures that by the time that we're looking in the deep crust, even if we've got good aeromagnetic data, we're just not going to be able to see that same fine resolution. And so it's that's why basically these structures using standard processing have been missed. But no, it'd certainly be worthwhile to look for more. And I'm just hoping that we can find some features perhaps at a slightly higher level in the crust that might be able to, elsewhere, that might be able to be imaged. But I just say that in looking at these features, I have actually looked at other concentric structures in the geophysics, such as the Richat in Mauritania and so on. And there we can also see in the geophysics data, especially in the aeromagnetic data there too, these much larger concentric features than just those that we're seeing at the surface with a Richat, again, associated with intrusions in that case. But yeah, it'd be great if we could look at some of these other areas, and if you guys have got any ideas from looking at like your papers on these dike swarms and so on Earth to use these data sets, it would be really good to compare even younger examples as well and what we're seeing in the geophysics.
Yeah. One final thing about the smaller scale structures. Some of those actually, we've got some mapping on some ones that are a couple 100 kilometers across. So that's relatively, that's on the lower side of the side. And some of those actually look like they're mega caldera sag duct, sort of sag style caldera, sagging of the roof, not so much ringed concentric structures. And it's sort of an interesting style that there's some kind of transition between mega caldera type features and large, super large caldera and small corona in terms of the process.
But in some of these areas where some people on Venus had been saying there's incipient subduction and some of these margins, but if we actually look, and that's we didn't have the time to go into, but the actual curvature of the coronas in the opposite sense than for the direction of displacement, that you wouldn't just geometrically being able to produce the same sort of subduction zone and arcs on Earth. The actual plate, if we call that a plate displacement, is exactly the opposite on Earth. And so, yes, it can start to be pushing downwards, but it's just geometrically just not feasible for that to develop into the same sort of subduction arc-related sort of systems as on Earth.
I like that assessment because that's sort of been in the literature recently, is that these are proto-subduction zones in these, surrounding some corona. And I see your point that that's not really maybe a good analog in terms of it transitioning from something that sort of has dripping down on the edges of the corona or downwelling to something that could develop into.
Yeah, so that's why I like, again, Taris's models, just showing, like you described, the dripping and sort of starting some downwelling, but I just can't see that evolving. And also, it's coming back to the idea of subduction zones, that, it's these drips that are dripping down, and they're not actually going to be pulling the plate with a behind it to continue plate-like motions like John was describing. So that again, as the sinking slabs are basically one of the motors for getting these plate motions in modern day plate tectonics, whereas the drips are not going to give you that. And so that's where looking at the distinction between modern plate tectonics and these ancient processes, we've got to make a distinction. We can't call it a steady motion, the plate tectonics, because of these rather important differences.
Mm-hmm. Cool.
Okay, I think Daryl Long had a question in here. How does the presence of predominantly south-directed flow of turbidites in the Abitibi and Pontiac fit with your model?
Frankly, I have no idea. I don't know, Jean, if you're listening, if you've got any idea on that. I've never looked at that.
Not really. I don't do sedimentary rocks very much, but relying on Nathan's paper, he had posited the Minto was uplifted and was feeding a lot of the stuff to the south. So it could be a local thing. You have an uplift to the north that's developing, and that's how I think it's mostly local.
The reason I ask the question is because it has a direct implication. Oh, I'm on here. The reason I ask the question is because it has a direct impact on your model, because if all the currents are coming to the south, it kind of negates the type of model that you're basically using a sort of an accordion type motion on that thing. So you should have an equal amount of sediment supply from the south as the north. So it means that it's a way of testing your model. That's why I asked if you'd looked into it.
No, I don't do field work on sedimentary rocks. So I've never actually thought about it.
Time you started.
You should start.
Yeah, no, and it's the same. I don't know.
More information in a centimeter of sediment than there is in a kilometer of any igneous rock.
Just looking at it.
Depends on your viewpoint.
Yeah, I don't know if Phil was just looking here. I mean, there's quite a few people, whether Phil
you live long
in the
enough to
audience.
learn that.
Yeah. No, but I mean, that's again something maybe, no, it's a good point then to think about. No, I hadn't considered sediments at all. I'm looking deep, and John's looking at the more the chemistry and the geology, but it was Phil Thurston in the early days that was sort of providing some.
Sediments tell you what was at the surface in the geological past.
Yeah.
You can't tell that from any other way.
Yeah.
And what it says is, there's hardly any andesite exposed on Earth in the past because it wasn't being eroded.
How do you know if you've never looked at the sediment?
Well, other people have.
But you don't know that literature because you don't care. You told me that.
Well, I have read some of it.
Yeah.
Believe it or not. And I actually have done some sedimentology, believe it or not.
Where are all the zircons coming from?
The TTG domes that are being exposed and protrude from the surface, as shown by Shufa Lin's study, where you can see the sequence of erosion reflected in the downside basin. Thing is,
most of the granites in the Slave Province are potassium feldspar-rich granites.
I'm not talking about
Most of the greenstones are sediments.
Yeah.
And they're quartz rich and they don't come from TTG.
Yeah, but that's where it would be really good to get some other discussions with people in all the different domains later on, because, you know, it's we've been focusing on certain things, and of course it's all these other informations is equally, or in some cases even more important. It's, you know, I'm just presenting one element, and when I'm saying against plate tectonics, it's just that I can't see the part that I'm showing there fits in with modern plate tectonics. And so yeah.
And there's as many detrital zircons taken from a TTG as a granite. They have about the same zircon content, so that's irrelevant, Paul.
Okay, should we move on to another one? We've got a question from Shufa. If the continental blocks in the Superior formed by rifting of a larger one due to plume, you would not expect the resulting block to be linear and thousands of kilometers long, as you see in Superior.
Sorry, I don't really understand that that question. I mean, Shufar, can you perhaps enlarge on that, what you're meaning?
Well, if you maybe I can put if you have a plume caused a rifting, you may have this triple junction, whatever. You would not expect to be this piece that get rifted away linear and extend for so long. And one thing that's impressed a lot of people in the Superior is that it had linear features. It's mostly east-west. Yes. And each sub-province lasts for, that goes for thousands of kilometers long. And can you explain that by your model? If you are looking at 3D, 2D, of course, you have this north-south section and things, everything seems to be ripped away, north-south direction in the current coordinates. But if you look at the 3D, each of them goes for 1,000 kilometers long, or at least hundreds of kilometers long. Would that be consistent with your model?
Well, it is consistent. I mean, that's precisely what we're showing is that it wouldn't be consistent. I agree if you were just looking at one big plume fragmenting, a continent. But here, the main point is that we're seeing several of the concentric features along the southern margin of the northern superior Proto-Craton, and so what we have is that linear rifts do form where you're linking these zones of mantle upwelling. And so if we had the main plume that we're interpreting, or at least I'm interpreting, they must lie further beneath the Superior Province and is actually providing probably the regional shortening that we're seeing. But rifting between secondary upwellings is basically, giving you such linear features. And years ago, we actually did some physical models of that in putting in a sandbox where we had heater coils in a glucose syrup underneath our model, and getting a series of plumes. What we were actually looking at was that same question. So I can send you some photos of those models, but we're changing the geometry of these mantle upwellings that we're simulating to look precisely at the geometry of the rifts that would be produced. And when you had aligned mantle upwellings, you were getting such regional rifts that extended well past the extent of the external, if you like, mantle upwellings, that they produce such regional structures. I'll send you a copy of some of those results. We were looking at that for a small project in an exploration company was looking at exactly at the geometry of plume-related rifts in the Archean for nickel exploration, for the geometry of komatiite flows.
But then in that case, you require multiple arrays of plumes because you have multiple ripped from north to south.
Not really, because again, if we, I just showed you for the Afar plume that these plumes are again being pushed horizontally by the regional mantle flow. And we've got many examples of that on Earth in the present day. And so that's where in that cartoon in Jean and my geology paper, we sort of showed that we can get these secondary and tertiary other upwellings, if we like, that we can be fragmenting continent still in a linear fashion. Of course, with all these questions and what we've done, we still need an awful lot more work, and we still need to get the modelers to be doing more numerical modeling just to see what is feasible and what is not feasible. And so there's some good points to follow up, but we're just in the early stages of proposing some ideas, so it's good to get feedback like that and to try and check some of these things out. But I personally just can't see any other way, at least, of explaining the features that I'm observing in the present models. So maybe there's some other model. I'm certainly open to that. or to better define our model. What the gut feeling also is that I was trying to get away from putting circles everywhere on an image. One can easily, if one's interpreting a magnetic or any geophysical image, get carried away and start drawing features which don't exist. And I purely limited myself to drawing those 4 major concentric features on the southern margin, because I could see that in 3 different data sets. All of those features I can see in aeromagnetics, gravity, and magnetotellurics. There are other possible features which I've wondered whether they could be other secondary upwellings further south, but I just haven't got the confidence to show, given the data, and I feel I'd be pushing my data too far to be drawing these features. But there's a couple of them that I'm wondering more about, because there's been a nickel discovery on the margins of one of what I thought was a possible upwelling zone, and that's directly south of the Ring of Fire. And the geophysicist involved in that discovery actually drew a concentric and linear features intersecting that feature, which was further south. So yeah, I might stick my neck out and draw a few more features, but at the moment I'd much prefer to build a model based on what I'm absolutely certain about.
All right, so John had a comment in here relevant to Shufa's question, so I'm going to read that. And then Paul has several.
All right, I could comment if you want, Alec.
Oh yeah, go ahead.
Yeah, Shufa, basically the southern superior is the southern limb of the outflow pattern. We think that the concentric structure of the superior itself reflects radial outflow. The northeast superior stretched east-west, the southern superior stretched north-south, and over in the H1EP is oblique. And then the southern superior was flattened over that. So we linearized a lot of these disaggregated blocks when that happened. That's my opinion.
And actually, going back to the constructions with Richard Ernst as well, that if we're looking at really at the big picture, we've got Cola Corelia abutting the Abitibi in many of the reconstructions. And if we look the origin of the belts, that if we continue the east-west belts from the what's now exposed in Canada in the Superior Province, they change dramatically in orientation if we believe the paleomagnetic based reconstructions with the Cola Corelia. So again, before seeing these concentric features in the Western Superior, I was wondering whether or not we had another mantle upwelling just at what was in the reconstructions, the junction between the Cola and Corelia, now the Ballamorian belt, with these east-west belts in the Superior. So we have to even go to even a lot more regional scale in putting back some of these other continents just to get the full pattern of these rifts.